Welcome to homework.
In this problem, we are given this information to describe a cell, and we want to find what the value is of the cell potential after the concentration of Zn2 plus changes by 0.20 molar. Based on this notation, these two lines in the middle represent the salt bridge, and everything to the left of those lines represents oxidation in the anode, and everything to the right represents reduction in the cathode. We know that the cell potential is always the cathode minus the anode. So we can first find what the value is of the cell potential at standard conditions. So starting with the cathode, the right side, we know that reduction will occur. So we can look up the table of standard reduction potentials and see that the half reaction that corresponds to that reduction in the cathode is Ag plus an electron goes to Ag solid. And from that table, we can look up the value of the standard reduction potential, which comes out to 0.80 volts. And now for the anode, we know that oxidation takes place. So for the equation, the half reaction from the standard reduction potential table, we know that we have to flip it so that we have Zn as a solid going into Zn2 plus an aqueous solution, plus 2 electrons. And so since we flip that for the oxidation, we have to flip the sign of the standard reduction potential, which was negative 0.76, so now it is a positive value. And now we add those together to get the overall cell reaction. And we multiply the top equation by 2 to cancel out 2 electrons on either side. And we are left with 2Ag plus aqueous plus Zn solid goes to 2Ag solid plus Zn 2 plus aqueous. And for the standard cell potential, we add 0.80 and 0.76, and that gives us 1.56 volts. And now we need to write out a reaction table to determine the non-standard concentrations that we have for each species, given the fact that we are told that we have 1.00 molar of both Ag and Zn2 plus, and we do not account for the solid species in our reaction table. And we know based on the stoichiometry that Ag plus changes by minus 2x and Zn2 plus changes by plus x. So the final concentrations will be 1 minus 2x for Ag plus and 1 plus x for Zn2 plus. Remember that we are told in the problem statement that the concentration of Zn2 plus changes by 0.20 molar. So therefore, x must be equal to 0.20 molar. And if that's the case, then the concentration of Zn2 plus is equal to 1.20 molar. And for Ag plus, it would be 1 minus 2 times 0.2, which comes out to 0.60 molar. Now we can write out the reaction quotient Q based on that overall reaction, which is the concentration of Zn2 plus divided by the concentration of Ag plus squared. And that is equal to 1.20 molar divided by 0.60 molar squared, which equals 3.33. Now we use the Nernst equation to solve for the cell potential at non-standard conditions. We know that the cell potential at standard conditions is 1.56 volts. Then we subtract 0.0591 divided by n, the number of moles of electrons, and we see that we had to cancel out 2 electrons when combining these equations. So that means n is equal to 2 times the log of Q, which we just found was 3.33. Now when we plug that all in, we should get a final answer for the cell potential at non-standard conditions after the concentration of Zn2 plus changes by 0.20 molar for the cell to be about 1.54 volts.